Okay, we should be live. Hello, everybody. Let's get the chat where it's supposed to be. Oh, and I need to share the text. There we go. And we need to be in the spot where we should be, which is the start of the X. There you go. So I should be ready. And I should probably, hi Cram, and I should probably put my microphone here. And I probably have to confirm, I think the audio is working. Okay, so we are all set. Okay, so today we are going to finally go into more details, more interesting things about the entropy. And we're gonna see how essentially with very little assumptions, we can bring in essentially we can tell what the entropy is and what are some basic axioms that it has to satisfy. And then we're going to be able to recover things like the expression for the entropy from these axioms that the entropy has to satisfy. So we're not going to just set some function and say, oh, there is an entropy and this is the function. We're basically saying we are describing ensembles. Ensembles are essentially collection of preparations, an infinite collection of preparation. Therefore, they will have some type of variability inside. They're not always the same. And we want to be able to characterize this variability of the preparations within the ensemble. And for this to make sense, for this variability to make sense, it has to satisfy a few conditions, and then we set those conditions as axioms, and we get everything else. So this is the part that we're doing today. And the interesting bit is there are some other works that people do, sometimes called the generalized probability theory or reconstruction of quantum mechanics and of classical mechanics. And one of the things that these people do have is this idea of a convex set where you put ensembles and do the mixtures. But they don't have an entropy associated with it. And what I realized when I was sort of figuring out what would be a minimal set of necessary axioms is that if you don't have an entropy, you don't know essentially whether your spaces are finite or not. So if you have the integer, the real numbers from 0 to 1, you have the open interval of numbers from 0 to 1, and then you also have the whole real line. You can make a map that maps to that interval in the whole infinite things. Topologically, you can't tell which sets are finite or infinite. And again, when you also go to the measure theory in the sigma algebra, you also can't tell. Like, these are just sets, and sets are mapped, and so you wouldn't be able to say whether you had an infinite position range that you shrank to a finite set of real numbers that are sort of a little bit degenerate there, because you took infinite sets and put in infinite regions and put them in a finite region. Or if you really had a finite region and you're stretching that region to infinity such that it becomes more and more spread out. And the entropy will allow you to know that, because if you have a finite region, the maximum entropy that you can get is the uniform distribution, and that uniform distribution is going to be finite if you are in a finite region, and you're never going to reach it. It's going to be infinite if you are in the infinite region. So the entropy actually it plays all these. It tells you what things are finite and what is not, and it basically tells you all the geometry. So it's kind of an essential ingredient if you're making a physical theory, because whatever information that you have about the geometry of size, at the end of the day, it's information about entropy, and you can go back and forth. So that's basically the motivation and why at a fundamental level you need an entropy, because the entropy is equivalent to be able to say all these things, and all these other approaches that they talk about generalized probability or they talk about reconstruction. If you don't have some type of entropic quantity somewhere, you're not going to be able to again to reconstruct the full physical thing, because you don't know what is finite and what is infinite. And the reason why this happened is because a lot of these other approaches, they really focus on the finite, not on the finite, on the discrete, when you have discretely many cases. And that's the simple case, right? And we want to be general, we want to be able to do not only the continuum, but also field theory. So you need something that actually allows you to go all the way through, and this is how you do it. Okay, so let's go through this carefully. And so this is the axiom of entropy. Every element of the ensemble is associated with an entropy which quantifies the variability of preparations of the ensemble. Formally, an ensemble space E is equipped with a function S that goes from the ensemble space to the real number, and it's defined up to a positive multiplicative constant representing the unit numerical value. Right, so this is a physical quantity, so you can measure the entropy in bits or in nats if you're doing some type of information theoretic things, or you can measure it in whatever it is in the international system, which I forget what the entropy, what the units of entropy are. And so we need in here, we need to know that there is an arbitrary effect with that numbers. And so all the whole physical characterization of the system should not be joule per Kelvin. Yeah, joule per Kelvin makes sense, right? Because what is it? Entropy times temperature is energy. So yeah, it should be joule per Kelvin. And so okay, so the whole system that we're doing has to be independent of the unit chosen. So we need to be able to take that into account. So the entropy has the following properties. And now instead of just going through one by one, which we did last time, we're going to go through one by one with the justification, because we need to justify all these things. And here we have a page and a half of justification. So we'd rather just go through it. Yeah, the Boltzmann constant is the conversion factor from like nats or bits to the joule per Kelvin. Yeah, that's basically the Boltzmann constant is just a change of unit. There's nothing intrinsically physical about the Boltzmann constant. It's just a choice of unit. So. I think in the international system, the Boltzmann constant at this point is just defined to be something, right? It's not a measure of quantity anymore. I forget. Anyway, I know h bar is now a set quantity. Is no longer a measure of quantity. It's just you choose the unit and you choose an h bar, and then you have the derived units. Okay, so let's go through this. The entropy quantifies the variability of the instances of the ensemble. Since the ensembles represents a collection of preparation of equivalent system, and since each instance will in general be potentially different, it is legitimate to ask how much variability there is among the different instances. Okay, so basically, you should really think as an ensemble as a collection, an infinite collection of all possible preparation. And are they all the same? Are they different? How much they're different among each other? That's basically what we're trying to characterize. So here we are assuming that the entropy is a quantity that is a linearly ordered property, meaning that it is always meaningful to tell whether one ensemble has more variability than another. If this is the case, the later requirements of continuity and strict concavity will force the entropy to be a real value quantity. And this is because the variability will change under statistical mixture. And since statistical mixtures are performed with real value coefficient, the variability will have to be a real value quantity. By the way, maybe I should share a link to the draft so that if people want to, look at it either during the live or later, they can. So let me get this link and put it in the chat. Okay, so hopefully that's basically instead of reading from the screen in case the resolution is not good, you can actually go and look. This is an auto-compile link, so you're always going to get the latest version. This is what I have on GitHub right now, and I'm working on this constantly. So every like couple of days there is a new push which update the text. So if if you open this link later and you see that the text has changed, for the people that are watching this not live, this is how it works. I might have made a change because we saw something and we changed it, and so you're going to see the newer and most up-to-date version. Okay, um, so the idea is that variability is assumed to be a linear ordered property, so that there is always, if you have to ensemble, you can always say whether one is more than the other. And whether it is conceptually possible to have a characterization of variability that is not linearly ordered, but still have a meaningful connection with statistical mixing is an open question. Therefore, we're not able to fully justify entropy's linear ordering at this time. So this is exactly the reason why we should try to make this justification, because sometimes when you write these justifications, you note, oh, this bit I can't really justify from first principle. There is a little bit of a hole. And this is the whole here. Like I can't be sure that there is a situation that I could say there are different ensembles, and of course each ensemble will have its own variability, but two ensembles are so different from each other that I can't even compare how these things are, variable, like the variability of one or the other. They're just totally different. They're incommensurable. And in a sense, this might be related to the fact that if you have 2 degrees of freedom, you can always map 1 degree of freedom to the other, and then you can define an entropy that is comparable, right? So it might be baked inside physics, the fact that these things somehow they are comparable. And I don't know whether it's because, again, if they're not comparable, I can't do physics, or I have no idea. And as Cram is pointing out, this may play a role if you want a more general theory that you want something that is really non-equilibrium. Because if you have two things and they're kind of going at equilibrium, probably there is an assumption there that you can trade sort of the variability of one state with the variability of the other, right? So that, this is more spread, this is less, and then they go to equilibrium. And so it might be that the assumption of being able to take things and put them in an equilibrium and connect them already tells you that this is the case. I don't know. There is probably more conceptual work to be done here. And so as I said, like very humbly, I say this is the whole. It might be fixable. It might be that one is able to make an actual justification, an actual make a first principle argument. Why, if you don't have that, you can't essentially do physics, and therefore you have to assume that. And or maybe you can't, and then maybe there is more interesting things that might happen. So Cram says, I could easily imagine a partial order where two different states have the same asymptotic equilibrium but aren't directly comparable. That may be quite a sensible thing to consider. That's exactly the type of thing that I'm thinking. Yeah, there are some, when you're coupling some system, there are some pieces that sort of do something that is together, that sort of goes together and that is comparable, but other parts of the system are not comparable because that they are just different and they're not even coupled. So I really don't know. And that's why these things are in the justification. So it's there. And if somebody wants to do the due diligence, you can say, aha, there is this hole, and either I try to close that hole, or I may try to find the new physics in that hole. Right now, I just say this is the case. So therefore, the linear ordering of the entropy should be considered an assumption. Provided that assumption, we are justified to assume the existence of a real value function that returns the entropy, a measure of variability of the ensemble. That's basically it. Okay. Since the entropy is a real valued quantity, it will have a corresponding unit. This unit is independent from all other units, and therefore the overall structure of the ensemble space must be independent of this choice. Mathematically, the physical dimension of the unit is not captured, it's just its numeric value. Its numeric value. A change of unit changes the numeric value by a multiplicative constant. Actually, a change of unit may change it doesn't have to, because it could just change the unit. Well, are two units, two units just differ by physical dimension? Yes. Yes, because I could, so I could have the Boltzmann constant. The dimension is energy over temperature, but I would be able to choose the joule such that the constant or the Kelvin such that the numerical constant is still one. So let's fix that. A change of unit may change the numeric value by a multiplicative constant. Let's see. This is take forever to build. Okay. A change of unit may change the numerical value by multiplicative constants. Since variability is an ordered quantity, we want the change of units to respect the ordering, and therefore it should be a positive multiplicative constant. This justifies that the entropy function is defined up to a positive multiplicative constant. So Cram is commenting, given that non-equilibrium is the bread and butter of biological life, it'd be extremely interesting to capture that as well, but it's by its very nature more complicated. Yes, so I'm not so sure whether if the assumption of linearly ordered would still apply if you say, okay, a biological system might not be comparable and so on, but there is a lower level of physical systems that I can compare. And so it might be that if you make that assumption, then the entropy becomes a linear quantity. So it may be that to not have a linear quantity, you have to assume that there is no lower level where things become homogeneous and comparable. And as I said, I have no idea. Yeah. Okay, so the entropy is defined up to a positive multiplicative constant, and now we have note that the additivity of the entropy over independent system fixes the absolute scale. This is something that somehow well, this is something that gets lost in information theory, because in information theory there's really no such thing as a absolute scale. The absolute scale comes from thermodynamics, but then when somebody does classical thermodynamics, since the zero is not well defined, it gets into thinking that the entropy is not absolute, is relative. But the problem is that it has to be absolute because it's additive over independent system. So if SAB is equal to SA plus SB, in fact, one can't rescale all three terms by an additive factor and preserve the relationship, right? So if you have this relationship that the entropy of the composite is equal to the sum of the entropy of the two subsystems, if you rescale the composite by one, and if you rescale all the entropy by one, you rescale this by one, this by one, this by one, then you lost the additivity. So yeah, the zero of entropy is actually an important feature, which then it's enshrined into the third law of thermodynamics, which basically tells you that there is a zero of entropy. And I don't know why a lot of people sort of seem to miss this bit. It's fairly important. Okay, so now the variability in the end will have physical consequences and it will therefore be measurable, thus experimentally verifiable, and then it will have a topologically continuous, it will be a topologically continuous function. This is because in the previous work, we showed that any a relationship between two experimentally defined set of possible conditions, then the function has to be continuous in the topology that is representative of how you measure and how you verify those possible cases. Another way to see this, moreover, small changes in the ensemble should produce small changes in the variability, which justifies analytical continuity, not topological continuity, but it's sort of they are related because the topology of the entropy is just going to be the one of the real numbers. Therefore, we're justified to assume continuity of entropy. So the first thing, the first assumption of entropy just comes from the fact that entropy is something that we can measure and we can see that there are consequences for it. Okay? So now we have to justify the second condition, is strict concavity, meaning that if you have the entropy of a mixture, this has to be greater or equal to the average of the entropy of the states that you're mixing. And the equality holds if and only if the two things, the two ensembles that you're mixing are actually the same ensemble. So this is what we need to check and verify. And it's going to be here, the variability. Okay. Suppose we have two ensembles and perform a statistical mixture. There are going to be three sources of variability. The two ensembles and the random choice at every instance. The total contribution from the original ensemble would be the average variability of the original ensemble. So if I have some kind of differences in ensemble on one, of differences in preparation for one ensemble, differences of preparation in the second ensemble, and then we are picking, right, the variability that we get for the fact that we pick those two particular ensemble is essentially the average of the two. We're picking one at random, so it's going to be the average. The total contribution for the original ensembles will be the average variability of the original size. This is increased by the variability introduced by the random choice, which is always a positive contribution. So if we have, imagine the case that we have two ensembles that are always preparing the same thing. So every time that I pick from here, you pick the same thing. Here I always pick a red ball, and here I pick a green ball. So there is absolutely zero variability from here to here, right? And so when I pick something, the contribution is not the variability of the picking is not going to be given by the variability of the ensembles themselves, because they have none. It's going to be increased by the choice of the two of the choice that we're making between the two ensembles. So this is increased by the variability introduced by the random choice, which is always a positive contribution. We can't decrease when we are making a random choice, we can't decrease the variability. We can only increase it. There is no way to make the spread narrower. Therefore, the final variability cannot be less than the average of the original ensemble. That is the entropy for PA plus P bar B, and I recall that P bar just means 1 minus P, so that we don't write always 1 minus P. This has to be greater than the average, the P, the entropy of A, plus P bar, the entropy of B. If we're mixing an ensemble with itself, this is equivalent to just choosing from the original ensemble. Therefore, the variability, it will not increase. So if we have two copies of the same thing, and we pick from these two procedures that are essentially equivalent, the variability is going to be the same. Conversely, if the variability stays the same, it means that the random choice does not increase the variability. And therefore, we must be choosing between equivalent ensembles that represent the same type of preparation procedure. Therefore, we are justified to assume that entropy is strictly concave. Okay, so this is sort of what we want to be able to do in physical mathematics. We want to be able to go and look at these axioms, which are the starting point for the whole system. And we want to be able to see that there is a well-formulated reason as why we take those axioms, because since everything else is going to depend on those axioms, we must be sure. So this is the way that this is justified. And Again, it might be enough justification for you or not. This is it always can be improved, but there has to be something like that. And this is typically not what is done in the foundations of physics. You just either take axioms because you like them, which it's a little bit random. Okay, now we are going to look at the upper variability bound. So we have a bound when we're doing a mixture from below, and now we're also going to have a bound from above. And the idea is that whenever we take a mixture, the entropy of the mixture is bounded from above from the entropy, the average entropy of the initial preparations, plus a contribution that it's dependent only on the mixture. So it's a pure contribution that just come from the random choice, and that only depends on the coefficient that we're using for doing the mixture. If the equality holds, A and B are non-overlapping or orthogonal, and we're noting A orthogonal B. And then the idea is that the function, again, is the same for all ensemble spaces because it depends only on the mixing weight. So a cross entropy term and the individual terms. Yes. So as we'll see now, what happens is that this is represents the variability of the two things that we're missing, and this is the contribution from the random choice. And okay, so it should be here. On the other hand, the variability cannot increase arbitrarily during a mixture. The maximum variability will be given when two ensembles are non-overlapping, when an instance of the first ensembles cannot be produced by the second ensemble. That is, a single instance is enough to determine whether we have the first ensemble or the second. So you have the ensembles, they prepare, their procedure, they prepare instances, and then you look at one instance. If you say, okay, this instance cannot come from this, always comes from this. And whenever you get an instance from the other side, well, it always has to come from this and not from the other side. Then we say that these ensembles are non-overlapping or orthogonal. You can also say that are perfectly distinguishable. I still don't know what is the good name that we should give, but the point is that you can always tell them apart. That's kind of the idea. And if that's the case, then in this case, the variability is increased by the variability of the random choice, which must depend only on the mixture coefficient and not the nature of the ensembles themselves. So the maximum is achieved simply because we have two things that are completely, you could tell them apart, and then the variability is basically just the addition of the random choice that we're put. Is IPP bar like the mutual information entropy? It will become the Shannon entropy. So later we are going to show that that I is a minus P log P minus P bar log P bar. And the cool thing is that we don't need to impose this. It is just the only function that can satisfy that. And we're going to go through the proof because the proof is very nice because it works, again, without knowing what type of ensemble space you have. So it could be a classical, it could be quantum, or it could be even something completely different that a new physical theory that we don't know. You still get the same function. Like there's no other thing. Like these axioms are enough to constrain the functional form, which is brilliant. Okay, so where were we? We were here. Okay, so a single instance is enough to determine whether we have the first ensemble or the second. In this case, the variability is increased by the variability of the random choice, which must depend only on the mixture coefficient and not on the nature of the ensembles themselves. That is, we have the thing that we said before, we have the entropy of the mixture is less or equal to the average entropy coming in plus the contribution of the random choice. So this is the upper variability bound, which is saturated if and only if A and B are non-overlapping. And so while before we had a notion of equality, right, that didn't come from the entropy, so we're saying the entropy must respect this notion of equality. Here we don't have a notion of when two things are completely different. And it's going to be the entropy that tells us when two things are completely different. And so we define things to be non-overlapping or orthogonal because they saturate the upper entropy bound. And by the way, we call these orthogonal because this is exactly what happened, let's say, in orthogonal subspaces, both in classical mechanics and in quantum mechanics. And when you have two outcomes of a measurement procedure, even two ensembles that are orthogonal to each other because they live in orthogonal subspaces, that's exactly when the entropy goes up by a full bit when you make an equal mixture of the two things. So we're basically, like later, we're going to recover all of these vector space structure decomposition in different subspaces from the idea that the entropy is maximized whenever you're doing mixtures. So yeah, that's sort of how it works. So we define things to be non-overlapping or orthogonal because they saturate the entropy. And the actual function I is left unspecified, and as we show in proposition 124, is wait, the actual function I is left unspecified, as we show in proposition 4. This is it will correspond to the Shannon entropy, as it is the only indication of variability that will satisfy the axiom of entropy. I didn't have a sentence. That's funny. That's kind of why I want to review this more publicly, because it forces me to actually double check the whole thing. And then you guys might see some things that I'm missing. Okay, so we have justified continuity, the strict concavity, and the fact that we have an upper variability bound. And now we have this last part of the axiom, that's the property of the entropy, that mixtures preserve orthogonality. That is, if we have A that is orthogonal to B, and A is orthogonal to C, and by orthogonal, again, we mean non-overlapping. These ensembles are totally different from each other, and they maximize the upper variability bound. So if we have A that is orthogonal to B and A orthogonal to C, then you also have that A is orthogonal to any mixture of B and C. And if A is orthogonal to any mixture, to a mixture of B and C, then it's orthogonal to A and it's orthogonal to C. And the justification is not very hard. Suppose ensemble A is non-overlapping with B and C. That is, an instance of A cannot ever be produced by either B or C. Then an instance of A cannot be produced by a mixture of B and C, since ultimately a mixture of B and C will return an instance of one of the two. Therefore, A is non-overlapping with any mixture of B and C. The argument... The argument works in reverse as well. If an instance A cannot be produced by a mixture of B and C, then it cannot be produced by either. And so this justifies mixture preserved orthogonality. Okay? So the whole idea here is, again, we have ensembles. Ensembles are collections of preparation. They are collection, therefore there will have some variability within this collection. And we are asking how much variability we have within this collection. And the variability has to satisfy these sort of starting points. And these are footnotes if you guys want to read them, but they're not critical, so I'm just going to skip them. And now, of course, we have we've put the axiom of entropy. We need to show that discrete and continuous classical ensemble spaces and quantum ensemble spaces satisfy the axiom of entropy. The entropy orthogonality, it's not about extensivity. So the extensive property of the entropy is on the product of what's it called? It's the product of system, which means composite systems with respect to subsystems. I haven't developed yet the product space for ensemble spaces. That is the the notion of composite system and how entropy is going to behave in those cases. It could be that orthogonality would lead to that, but the problem is that it's a different type of orthogonality. So here we are talking about the so if you imagine, let's say two variable, x and y, right? Here the orthogonality, it's about the support on a single variable. So the entropy will have this 1 bit increase if we're mixing things that have disjoint support. The other type of orthogonality comes when you have distributions that are the product of the distribution in X and distribution in P. And I'm pretty sure that there's going to be a connection between these two things, but it's going to be highly, how can I say, non-trivial, right? That's sort of that there is a lot more to impact. As someone with an engineering background as someone with an engineering background, I'm having a big trouble going over the assumption of physics book. What prerequisite do you recommend? Which part are you looking at? The physical mathematics or the reverse physics? Or both? Okay, beautiful. Okay, so for the first part of reverse physics, where we go through what's it called? Through classical mechanics, the issue there is that since we want to go through the whole math, the correct setting for looking, well, first of all, you will need to know the three different mechanics: Newtonian mechanics, Hamiltonian mechanics, and Lagrangian mechanics. If you've never seen those, it's gonna be very, very hard to be able to go through that. When you are inside that part, the first part, when we treat the first degree of freedom, I think that if you just have, if you know a little bit of the fact that there are the three different mechanics and how they kind of relate to each other from a textbook, and you have a notion of um, partial derivatives, right? That and curl, divergence, and so on. You're going to be able to reach, I would say, without too much struggle in. Oh, mamma mia, I'm losing my voice completely. You're going to get through the 1 degree of freedom. The problem of going from 1 degree of freedom to the general degree of freedom is that you need to know some notions from differential topology. You need to know essentially what forms are and what an exterior derivative is. The problem with that is that if you look at how that's done, and even just the mathematical notation that is used in those textbooks, it's very abstract. And it took me like 2 years to actually reverse engineering that math to be able to give it physical meaning. And I had to come up with a math notation that is sort of more similar to what one use um, in physics when you're doing general relativity, essentially. So I made an extension of the Einstein notation so that we could also talk about the exterior derivative and stuff like that. I am fully aware that the prerequisite to be able to follow everything are nuts, and I, I don't know. So it's kind of like we would have like it would be a good project where people could contribute to work with me to create some sort of primer that gave you all the background that you need from all the different areas. Because I can't just tell you, oh yeah, you need a little bit of differential topology, because then you go and look at a book on differential topology. There is like this pages and pages amount of things, and most of them are going to be irrelevant because you only need maybe like 20 pages, but the right 20 pages. And And the notation is still going to be very hard to swallow, wherever our notation is going to be more similar to that. Then in that same chapter, we also go through like relativistic things. So if you've never seen special relativity, also that is going to be a hard time because there be concepts from there. But then again, if I just told you, oh, look at this book on general relativity, you're going to be lost because there are so many things that it would be a one semester class. Like I can't tell you that you need a one semester class in Hamiltonian and Lagrangian mechanics, a one semester class in general relativity, a one semester class in topology, and so on. And like that's kind of the issue. And so it's difficult for me to tell you where to look at this stuff. So when I have students, I usually give them like one or two like mini lecture on this. I mean, if there is enough interest, if there are enough people that are interested in doing this, we could have a separate cycle of lives where we go through these things. And then that could serve as the primer for the other people that come in. It would be a little bit of work, but again, if there is enough interest, we can also do that. That probably is the simplest way. So I know a little bit about Lagrangian Hamiltonian mechanics, but not formally. So if it's any consolation to you, most of the stuff that I learned of Hamiltonian Lagrangian mechanics and even quantum mechanics, I actually learned out of curriculum. I just read books. A lot of the things that we use here in order theory, I just read books, and then I got myself the competence to then be able to talk to colleagues that actually work in these areas. So the good news is that in principle, it's not that hard to get that background, but we're not gonna I don't know if it makes sense. You're not going to find the little bit that is saying, oh, you only need to do this, but we could create it. It's the same thing with physical mathematics. Like in principle, you need a little bit about, mathematical logic, but you don't need that much mathematical logic because, they go and do some construction that are not going to be useful. And you need to know some topology, but not that much topology. And okay, so let me see. Cram is bombarding me. Let's say, remember when I first started Newtonian mechanics, I felt very absent and I had to get used to the notion of functor calculus. I was thinking a bit on my way, therefore making assumptions. I guess it might be at some point makes sense to write books that are designed to be prerequisite for this one, but you first need to have it fairly finalized so you know what those things might involve. Yeah, that's why I think that the lives work better because it's less work. And since back when I learned it, online research and only sorry, have hugely improved. And that's the other problem that I also have. Back then, it was hard to find anything reasonable understandable on Hamiltonian mechanics, but today, so right. And so there might be already sets of videos on the internet that would allow you. Maybe you can have a recommended reading list. Do you have notes on what books and what chapter in them particularly helped you? Let's see. Sorry, a lot of that was meant at Microsoft. No, yeah, no, I understand, but I wanted to sort of review them. Yeah, so if we had a set of introductory videos of things that are related to the project that put you already in the right frame of mind, that's great. My only worry is to have something that it's then too big, like you find courses of line on advanced mechanics. I think that would be too much, right? You find courses of line on topology. I think that would be too much. So I don't know exactly what. But yeah, so if other people see this live later and think that it might be useful to have other lives where we do sort of bare minimum of Hamiltonian mechanics, bare minimum of Lagrangian mechanics, bare minimum of special relativity, a bare minimum of differential topology, and so on. I can then ramble for an hour with maybe a tablet. I would just write on a tablet and tell you these are the pieces that you sort of have to have in your mind. Because even there, the most difficult part, it's sort of having the scaffolding where you can put the pieces. And then you can go and even look on Wikipedia, look here and there, and then fill in the scaffolding. But at least you have an idea of what these tools are there for and why they're useful and what are the main results that you should be looking at. Okay, so I don't know if this was helpful, the Markov. Hopefully it was. Okay, so let's go back to the book, and now we're going to prove that classical ensemble spaces actually satisfies the axiom, right? Because if they didn't, we would have a problem. So let's first look at the classical continuous space. Every ensemble is represented by a distribution rho of x with the integral of rho x over the whole space equal to 1. So the entropy is given by S of rho equals minus the integral of rho log rho over the space. This is a continuous function of rho, so we have verified that continuity. Now, to show strict concavity, note that minus the logarithm of x is always greater or equal to 1 minus x over logarithm of 2. Okay? And this is because this is essentially the tangent at when the entropy is 0, and then the entropy is sorry, the logarithm is strictly concave, and so it does this strictly convex. Minus the logarithm is strictly convex. Okay, so to show strict concavity, note that minus logarithm of x is always greater than 1 minus x over logarithm of 2, with the equality holding if and only if x equals 1, if we're here. And so we have the integral of the mixture is just going to be the Shannon entropy of the mixture of the distribution. So it's going to be p rho 1 plus p bar rho 2 logarithm of p rho 1 plus p bar rho 2. What we're going to do here is just we break this. This is the sum, so we break it into 2 logarithms. And now we do this trick where we take the argument of the logarithm and we divide it and multiply it by rho 1, and we multiply and divide this one by rho 2. And then since the logarithm of the product is the sum of the logarithm, this rho 1 goes out of here and becomes its own thing. Okay, so we have this term that is just the sum of this is just this, and we have these two terms whose sum is this. And you already see the trick, right? Here we're getting a rho 1, rho 2, rho 1 log rho 1, here rho 2 log rho 2, right? So we're going closer to what we want in the end. And now we have this, and now we're going to use the property that we saw before, that minus the logarithm of x is greater or equal to 1 minus x. So this is logarithm of x. This is the x of the logarithm. And so this is going to be greater or equal to 1 over the logarithm of 2, 1 minus the argument. And the same thing for the other one, right? And now we do more trickery here, if I remember what's going on. We are essentially collecting, let's see, this part. We're collecting this part, and we are rewriting it a little bit different. We have the 1 here, right? This one is going to be multiplied by rho 1. So this is just the integral over rho 1. And this is just going to be multiplied by rho 1. So the rho 1 simplifies from the outside. And so it's just the integral of p rho 1 plus p bar rho 2. Okay? And the same thing for the other side. So now this becomes simply the p times the integral of rho 1 minus the integral of the mixture. These are integrals over probability distribution. So they're just 1. So this is equal to 1. This is equal to 1. This integral is equal to 1. This integral is equal to 1. Therefore, these go to 0. They go away, and you just get the sum of the entropy. So the entropy of the sum is greater or equal to the sum of the entropy. This is a kind of, it took me a while to figure out what are the right bounds to make these things. I mean, if you look in information theory, books, they all use a different type of things. And I found that this is actually having clear that there is this bound on the logarithm helps in so many calculations when you're doing information theory that it's very nice. And so this is the strict concavity. And now we have to do the upper variability bound. And first we have to show that the equality holds only when this argument was 1. But then this argument is 1 exactly when rho 1 is equal to rho 2. Because you need to have the average, the final distribution has to be equal to 1 of the distribution. And this is going to be equal only if rho 1 and rho 2 are equal. So you get the strict concavity. Now for the upper bound, you can show that the logarithm is a strictly increasing function. Well, the logarithm is a strictly increasing function, and therefore we have that the minus the logarithm of x plus k, which would be here, is greater or equal to minus logarithm of k. So if we are here, minus logarithm of x minus logarithm of x plus k is always greater. Is always less. It's less, not greater. It's greater because there will be a minus sign. So if you increase the x, the minus the logarithm goes down. And these two are going to be equal only if k is equal to 0, right? So if this positive k is brought to 0. So this is the other thing that we're going to use to make the upper variability bound. And this is how it works. We have again the entropy of the mixture, which is just the Shannon entropy calculated where on the mixture, so both inside and outside of the logarithm. And again, we can break this into two things because this part is just additive. And then what we're going to do is that on this side, this is going to be the k, because this is always a positive number that we are adding. And so the logarithm of minus the logarithm of p rho 1 is always going to be greater than minus the logarithm of p rho 1 plus p bar rho 2. And on the other side, we remove the rho 1, because again, this is going to be the k, and so this is always going to be greater. And now, of course, we remove the right thing. So now we have a rho 1, and rho 2 here. But we have the p's inside, pesky p's. So we need to take the p's out. And again, we do it because the logarithm of the product is the sum of the logarithm. So you're going to have one logarithm with just the p, one logarithm with just the rho 1 logarithm with just the p bar, and one logarithm with just the rho 2. So these two parts, right, become these two parts that become just the entropy of the two distribution. And these other things, you can take now the log p outside and the p outside, because these are just constant, and you are just left with the integral of rho 1. But the integral of rho 1 is that the integral of a probability distribution is equal to 1. So you just get the p minus p, and you just get the p minus the minus p log p bar on the other side. And this is just the upper bound, the sum, the average of the entropy plus p minus p log p minus p bar log p bar. And that's, of course, a function of just p, and therefore we are satisfying the above axiom. The equality only holds if rho 2 is 0 whenever rho 1 is not different from 0, and whenever rho 1 is 0, whenever rho 2 is not the same as 0. And that is, the equality holds if and only if the distribution have disjoint support. Therefore, orthogonal distribution are exactly distribution with disjoint support, and that's how it works in classical information theory. If you take these two distributions that are defined on different regions, and you make a mixture, the mixtures gives you the maximum increase of entropy. And then the last bit, you have to show that we have that mixtures preserve orthogonality, that we have two things that have disjoint support, and you make a mixture, then anything that had disjoint support with the first has to have disjoint support for the other. and that's easy to show. Suppose that rho 4 has disjoint support from rho 1, which is equal with the mixture of rho 2 and rho 3. Then it has disjoint support from rho 2 and rho 3 because support of rho 1 is the union of the supports of rho 2 and rho 3. And conversely, if rho 4 has disjoint support from both rho 2 and rho 3, then rho 4 has disjoint support from rho 1 as well, and therefore mixture preserves orthogonality. All these arguments are valid for discrete classical ensembles, changing integral to sums. And we specifically did it with the integral first because going from integral to sum, a lot more things just remain the same when you go from sums to integral. That's where you have to be careful. So you make the proof for the integrals and then the sums come back. For the quantum case, instead, if somebody can contribute a short proof for these things, it would be nice, but I wasn't able to find a short proof and I wasn't able to take the ones from standard books that would fit nicely in a page. I always like to have all the proof reposted in the book so that, again, you don't have to hunt things in 3 million different books. And also it gives me a way to typically find the sort of the simplest proof that one can make for this, which is both fun and useful. It makes you more aware of how the math works. And again, I wasn't able to do it for the quantum case. I spent like a couple of days, wasn't able to. This, if somebody can help me doing that, that would be greatly appreciated. Otherwise, there are references in the literature that shows that that those things are valid, that those axioms, which are theorems in quantum mechanics, are actually satisfied. So that works. That tells us that we have these things. So I don't know if going through the proof is too boring, but to me, it's kind of useful just to make sure that the proof works, have other people look at them. And I do think that going through the proof, it sort of gives you a more of an idea of what the math is all about and how it works. So I think it's useful and it should be done. So we still have enough an hour. If there are no other questions, I would go through the proof that I actually corresponds to the Shannon entropy, because I think well, it's a cute proof, but also it shows you that there is a necessary like we need that functional form. It's not that roll or grow comes because somebody made some kind of decision, especially in information theory. People are used, oh, there are lots of entropy. There is the Renyi entropy. There is a whole family of entropy for every alpha. And the point is that physically, this is the entropy that you are mostly interested in because it has this feature. And it's important to show that it's the only one that has this feature. Okay, so we now prove that the function p bar must be the Shannon entropy. So the entropy of the coefficient p bar is the Shannon entropy. That is, p bar is minus kappa p log p plus p bar log p bar, where kappa greater than 0 is the arbitrary multiplicative constants for the entropy. For a mixture of arbitrary many elements, then this becomes minus kappa p log p. And this is why we had to say in the axiom that the entropy is defined up to a multiplicative constant, because when we go and find it and calculate it, actually it is. So this is how it works. Since the upper entropy bound has to be the same for all spaces, let us assume that E, the ensemble space, is such that it contains countably many orthogonal ensembles. So we have all these ensembles that go from 1 to infinity, and they're orthogonal, meaning that, again, when we put them together, they satisfy the, when we create a mixture, put them together with a mixture, they satisfy the upper entropy bound. Since the mixture preserves orthogonality, for any convex combination sum of PAI of finally many AI within the ELs, then we have that the entropy of the sum of the I is the I over is some function of all the coefficient plus the sum of the average of the entropy, where IN is a function of the coefficients only. Like we're combining things more than one. Note that given commutativity, the order of the PI does not matter, And since the coefficient can be zero, we must have that the In for P1 to Pn is equal to In plus 1 with Pi from P1 from 2 Pn with an extra zero added at the end. Therefore, we can think it as I as a function of the coefficient and write I as the function of the set of coefficient from 1 to 1. We now show that the I of 1 over n taking n time is equal to kappa logarithm of the n with kappa greater than 0. That is, the maximum increase of entropy for a uniform distribution is proportional to the logarithm of the number of cases. Okay, so this is the first bit that we have to show. So we pick two positive integers n and m. And we pick n times m elements inside those infinitely many orthogonal one. So we pick an ijk, where j is from 1 to the n. So this j goes from 1 to the n, but the k goes from 1 to the m. So this is really just the product of the two. So if n were 3 and m were 2, then this would be 6 elements. And the j would be 1, 2, 3, and the k would be 1, 2. So now what we do is calculate simply the entropy. So now we have the entropy of an average, a uniform mixture of all of them. And so we take every element, we sum it with a weight that is 1 over n times m. And this is the mixture of all of them, right? So it's the I over all the coefficient. So again, if n and m are 3 and 2, this would be I of 1/6 taken 6 times. And then we have the average of the entropy. So we did this by doing one step. We saw this as a single sum, and we just broke the single sum with just one mixture. Now what happens is that we can see this sum as a mixture of mixtures. So we first mix the m's, right? And then we mix the n. So if we do it that way, then first we are mixing these parts. So the coefficient become the 1 over n times. And these are now the things that we are averaging over. And so we have that we have the increase given by 1 over n. And then we have the average of the entropy of all the others. And now also this now, it's the entropy of a mixture of something. And so we can break this down again by taking the entropy of the coefficient and the average entropy of the entropy that goes in. Now we do a little bit of math here. You see that there is this is going to be a constant. So it's going to be a constant times the sum of 1 over n time. So this would be 1. So this just is I applied to I over m. And this becomes just the sum as we had it before. So now what happens is that this term and this term have to be equal to each other. Note that f of n, defined to be I of 1 over n taken n time, is a function of n only, and that fn times m is the sum of f on m plus f of m. And since f is continuous, we have that f of n is to be the logarithm times a multiplicative constant. And since the entropy is strictly concave, then k must be positive because the logarithm is a strictly concave function. Therefore, you have that the entropy of the coefficient of 1 over n taken n time is kappa logarithm of n for some kappa greater than 0. So that's the first bit. And now we use the second bit to demonstrate that the entropy over the rationals has to be p log p, minus p log p. And the way that you do it is basically, you can imagine that you have a bunch of fractions, right? You can now take those fractions and bump them down to a uniform distribution, such that if you have the 2/3 of something and 1/3 of something, well, that 2/3 you can break it down as a 1/3 plus another 1/3, right? And so if you do that, then you can take something that that is not a uniform distribution, but put it as a uniform distribution with different repeated elements, essentially. So you take something that is not a uniform distribution and you make it a uniform distribution by having repeated elements for the things that has to count more than one element. So mathematically, this is how it works. So let pi be rational coefficients for a convex combination. And we can write them as pi equals mi over m, where mi are integers, positive integers, and m is the least common denominator. So we're writing this, the rational coefficient, we write them as a ratio of integers. Since pi are coefficient of since mi is a positive integers, we can write that mi is the sum of 1 from 1 to mi. It's basically the sum of 1 mi times. And this is where we are taking a number and then we're making it a uniform distribution of ones. We now take M orthogonal ensemble Aij, where I still goes from 1 to n, so it represents the coefficients here, but J goes from I to M1, Mi. So we take as many elements such that we take, 3 over 10, so we take 3 so that we become 3 tens, 1 tenth. And so we have that the entropy of the whole thing is still the mixture of all the elements weighted down by m, right? So if, as I said before, let's say that we have 2/3 and 1/3, then m would be 3, and the first coefficient would be 1, 2, and the other one would be just 1. And so this would be 1/3. And so this, the entropy of this would just be the entropy of 1/3 taking 3 times. So all the flattened distribution. And the sum, again, of the entropy, the average of the entropy that we had before. And we know from before that this, since it's just the entropy of a uniform distribution, is going to be k log m. And as we said before, as we have done before, in the same exact way, we can write this now as the mixture of mixtures. So we take first these mixtures and we go back to the coefficients that are actually the fractional coefficient, and then we make a mixture with the fractional coefficient. So this, again, it's going to be equal to, first we break it up here, so we have the entropy defined on these coefficients, plus the average entropy on all these elements that we're summing. And then again, this is another entropy that we can break down. So we're going to have the entropy of this coefficient plus the average entropy here. Same trick here, when we are summing these are a constant. So we have the sum over m minus m of this, but now this does not sum to 1. This is going to sum to whatever is the coefficient. And here we have the other part, but this part here becomes the same part as this one. And now we have the two parts here. Instead, we have the uniform distribution that we had before, and this other part that becomes these little bits of uniform distribution over the different cases. And this is going to turn out to be pi k log mi. Right? It's this part because this is just the entropy of a uniform distribution. So as before, we have the last bit here is equal to the last bit here. And the bits in the middle, the k log m, has to be equal to the entropy of the coefficient plus this pi k logarithm of mi. And you put it together, you just do a little bit of math. This is the part that we're interested in knowing what it is. We put it on the other side. Then you stick here a sum of pi because this is just a 1. So we can just put a 1 here. And then we just do the logarithm of, this is a difference. So it's that this is going to be the logarithm of the logarithm of the different is, no, the difference of the logarithm is the logarithm of the division, the ratio. And so you get a ratio here inside, which is mi over m, because you have the mi here and you have the m here. This is just the p, and so you find that the entropy of the coefficient is actually minus kappa pi log pi. And again, the cool thing here is that we have no idea what kind of ensemble space we are in. We just use for these general definitions that are in principle justified for any physical system, and you get still the same function. Then the last bit that you need to do is that you need to take these coefficients and say that are not necessarily rational, that they're real, but I is continuous, and so pi can be approximated with rational values to an arbitrary level of precision, and therefore you're going to get the same function. And in the case that n equal 2, the one that we actually have to use in the definition, then this is just going to be p minus kappa p1 log p1 minus kappa p log p2. So again, this convinces us that the entropy that shows up in information theory, that shows up in statistical mechanics and so on, it's there for a reason. You need that because you need this particular functional form to describe the variability of the element within a distribution. And it's something about physics. It's not something about a specific physical theory, which is the important thing. And the last tiny bit of the section is that the unit for the entropy is determined up to the physical dimension by the maximum of the entropy of the coefficient. So if we know that the entropy of coefficient for 1/2 is 1, then we're measuring the entropy in bits. And that's basically what we're going to do for the rest of the work if not otherwise specified. And the proof is just simple. Rescaling of the entropy will also rescale the entropy of the coefficient. Therefore, setting the value of the maximum of I will set the arbitrary multiplicative factor. If I for 1/2 and 1/2 is 1, then k is equal to 1, and the logarithm is base 2, which corresponds to the entropy measured in bits. Note that this does not fix the physical dimension of the entropy, only the numerical value. And so that's basically the really fundamental stuff about the entropy. And I might, this is just, yeah, we can go through this because it's not, but I'll stop for like a minute in case there are some questions or note. I just find that this is absolutely cool that you can prove this. So. Ah, okay. So if there are no other questions, I think we're going to do this and not the next one, because the next one is going to be, this is actually something that I haven't reviewed yet. It should be, there should be a preamble here that I haven't written. But one of the things that you can show is that essentially there is a relationship between orthogonality and separateness. The fact, if you remember, two ensembles were separate if they don't have a common component. If you can say that there is a third ensemble and both of these ensembles can be seen as the sum of that ensemble with something else. And the interesting part is that in classical mechanics, this notion of separateness, whether you can find parts of the ensembles that are common or not, and orthogonality are exactly the same thing. And that's really what tells you that the space is classical. In quantum mechanics, this is not the case. And that's what becomes unintuitive in quantum mechanics. So you think that if you have if you have two things that you can't find a common component, then they're completely different from each other, right? So you have two pure states in quantum mechanics, spin up and spin right, right? There is no part that is common to both of them. And so you would think that these two things are completely separate, not only separate, but they're orthogonal, and you can have an experiment that tells you, "Oh, I have spin up or I have spin right or spin left." And that's the part that actually fails. The fact that you have two ensembles and there is nothing that is a subcomponent is not enough to tell you that the two things are orthogonal. But what happens is that the opposite is true. If two things are orthogonal to each other, they when they mix, the entropy is maximal. Then they can't have a common ensemble inside and see that those two things are the sum of the other. This interplay between separateness and orthogonality, it's basically what makes all this structure richer and what makes it so that it can have both classical spaces and quantum spaces. So that it's physically it's important. And I'm only like right now starting with having this concept in my head and playing with them and so on. And I think it's one of those things that once you have uh, had them crisp in your head, there are a lot of things that sort of become a lot obvious. Yeah, you see, this is why that smells of orthogonality being related of extensiveness. So I think there is a relationship, but it's not like because there is going to be a different notion of orthogonalities, which I probably will call independence. And it's like it's like another orthogonality, but on a different mathematical structure, right? So I agree that it's related, but it's I haven't teased out exactly how because I haven't done product spaces yet. The spin up versus spin right goes into how you can always find more information quantum mechanics, and yet you can only ever have a finite amount of information. Yeah, but you also destroy the information. So uh, like if you go from spin up and spin down, you didn't really, so, if you go from, if you have a preparation in up and then you prepare spin left, the new information that you get, it's not about the original system. It's about the final system. So it's like you're creating more information, but it's always about something else because the maximum information that a particular system can have, it's always the same. It never changes. And anyway, they're going to be related things. But let's go through this proposition. So ensemble is not orthogonal with itself or with its own components. Two orthogonal ensembles are separate. That is, if A is orthogonal to B, then A is separate from B. To show that every ensemble is not orthogonal to itself, let A be an element of the ensemble space. We have that the entropy of the mixture of A with itself is S of A, which is strictly less than the upper bound. Therefore, A is not orthogonal to itself as it does not saturate the upper bound. That is very good. Now, to show that every ensemble is not orthogonal to its own component, let A equals probability of B plus probability well, that's A equal P B plus P bar C. By mixtures preserve orthogonality, we have that A is orthogonal to B if and only if B is orthogonal to B and B is orthogonal to C. But B is not orthogonal to itself. Therefore, A and B are not orthogonal. Simple proof. To show that orthogonal ensembles are separate, we demonstrate the contrapositive. And by the way, this was a thing, the fact that if two orthogonal ensembles are separate, I had it as an axiom originally. I thought that it was an independent thing. When at some point, when I was rereading the justification, I said, wait a minute, I can prove the contrapositive easily, and therefore this can't be a separate axiom. So to show that the orthogonal ensembles are separate, we demonstrate the contrapositive, that ensembles that are not separate are not orthogonal. So let A and B have a common component. That is, yeah, it's always nice to get rid of axiom. That is, A is equal PC plus P bar D, and oh, this should be a lambda because this is not necessarily the same P. It's always interesting. Like you can look at your proof a million times, and you can always find something that is. Have you guys ever heard of rubber ducky debugging? Is this technique where you have a problem in a computer, you know that you have a bug, and so you read the code and you explain it to a rubber ducky, and while you're explaining to the rubber ducky, you're gonna realize what was the mistake. That's basically what we're doing right now. Okay, so we have. Why was that part highlighted? I made a change here. Okay, so let A and B have a common component. That is A equals PC plus P bar D, and B equals lambda C plus lambda bar E. By mixture preserved orthogonality, A is perpendicular to B if and only if A is perpendicular to C and A is perpendicular to E. But C is a component of A. Therefore, they are not orthogonal. Therefore, two ensembles that have a common component are not orthogonal. This means that if two ensembles are orthogonal, they cannot have a common component, and therefore they're separate. And then another thing that we can do that is going to be useful later is that we expand the notion of orthogonality to sets. So if you have two sets, you say that they're orthogonal only if the elements are all orthogonal to each other. One element of one set is orthogonal to all the other elements. And this is what is going to allow us to create the orthogonal subspaces later. So I would stop it here and see if there are any questions. And again, if people are watching this later, I'm always encouraged to put questions in the comments, and I'll be sure to respond. So I assume, Crime, you like going through the proof, right? It's fun. I personally like it. I don't know if there are other people on that says, "Oh no, that's too boring," but I think it's useful. Good, Tobias. Yeah, I mean that's kind of why I created the separate channel. So I said, well, if you lose the audience, we this channel is dedicated to go in depth. Uh, so if you're coming here and expecting just shallow explanation, then you're probably on the wrong channel. So yeah, no, it's in foundational stuff. It's kind of that the issues that. I have found that there are a lot of actual problem in these type of detail level that are just not looked at, because again most physicists like to talk and discuss upper level thing, but then like, it's like if you haven't cleared up all these little issues, it, everything becomes more murky if you go up, if the little details are not right. And then it's like trying to create a big computer program where the basic interfaces are buggy. Like you're not going to be able to do it. It's all going to collapse. So okay, so we ended here. And by the way, going back to the comments for Microsoft, if people have ideas or if people want to do lives where we go through the either prerequisites or more in general, more details on the physical mathematics part that it's already done, I'd be happy to set up. It's just that I wish that there are at least that I know there are at least, I don't know, 3, 4 people that are following and that are interested, and then I'll do it. Because if it's just me, like the problem with YouTube is that most people are also shy at commenting, so I never know how many people are actually there, looking at things, being interested. If I had, 5 people that say, "Oh yeah, yeah, I know, we're absolutely interested," and they're there, and they sort of like see that are always there, like you guys are here for this, that then I would certainly do it. So yeah. And it would also be fun because yeah, I don't know, like yeah, I don't know. And if there are enough people interested, please let me know, and we'll figure out what might be useful, and maybe other people can also contribute things, and we can have a more open discussion on other prerequisites. So that would also be great. Okay, so we'll just end it here then. We are 5 minutes to the half hour, but that's good. So thank you again for enduring this, and I'll see you next time. Bye, guys.